Hello, today I will show you how to find the formula for the pressure drop of a power law fluid. Just for context, what that means is if you have a pipe, which is circular, and you have a fluid moving through it, which is non-Newtonian, and specifically which is a power law fluid, then it's going to have a certain drop of pressure because of the viscosity. We want to find this drop in pressure, and now I'm going to show you how to do that, starting from the Navier-Stokes equations. Step 1. I'm going to write the formula that most of you have probably seen in your fluid dynamics class or maybe in a book. On one side we have the material derivative, where u is the velocity field of the fluid, and on the other hand we have the gradient of the pressure divided by the density, the viscosity term, the gravity, or some acceleration. So this is the formula, and you can use it for incompressible Newtonian fluids. But we want to find the pressure drop for a non-Newtonian fluid, so we can't use this formula. And there are some simplifications which we can do, right? Because our problem is in steady state, so it's not changing over time. And this part here, it's a bit long to prove it, but basically it's equal to 0 because the only velocity term is in the direction of the pipe. Since we're in cylindrical coordinates, actually, we have radial and axial direction, and we only have velocity in z. Everything else is 0. And the velocity in z only changes in the radial direction. And given this, well then this term is 0, this term is also 0. There's also no gravity, we don't consider that in this problem. Okay, so now all we're left with is this, but this is for a Newtonian fluid, so we need to make some tweaks. We can also cancel out the density, and we can rewrite this as the normal stress plus the shear stress. I forgot where I found this, but it works. Yeah. And we can rewrite this as one big stress tensor. Okay, so now we have this this equation, and we can simplify it. Of course, we're in cylindrical coordinates, so it's going to be a bit more complicated, but the sigma, the stress tensor, we expand it as this. Okay, and if we look into each of these terms, we see that actually most of them are 0. The only pressure gradient, we're going to say that it's in z, in the actual direction, right? This is going to be minus p, because of the minus sign here. The other term, which is not 0, is sigma zr, which is the shear. When the fluid is going at different speeds in the pipe, this creates a shear force. So you would have something that looks a bit like this. Here's your pipe. Here's the velocity profile, u. There's a condition that on the edges of the pipe the fluid is not moving. And the shear would look something like this. Because the fluid is not, the velocity is 0, well then there's no shear in the middle, which is going to be useful for later. Okay, so knowing this, we can rewrite our tensor, our matrix, like this. Now we need to do the tensor divergence. In cylindrical coordinates, the formula is a bit long, but here it is. I got this from a Wikipedia page, and I'll put the link in the description. The second line, I'm not gonna write it out because everything goes to 0. Now the last line. This is all equals to 0. So in the first line, you'll also notice everything is 0 except this, but actually it's also 0 because the stress, just like the velocity, is a function of the radius r. So this is 0. So all of this is 0. And we are left only with this last line. Okay, so plugging in our variables. This is 0. This is minus p. So this is starting to look a bit more familiar. We have the gradient of the pressure along the pipe. We can rewrite this in a simpler way. Since this is only a variable of r, we can use the normal derivative. And here we have 1 over r, which is equal to g. I'll denote the pressure gradient as g. Okay, now we have first order differential equation, which is linear and non-homogeneous. So this is quite straightforward to solve, right? We can use the method of multiplying like this. We could also just plug in the direct formula, but I'll do it the full method for those who don't know. Okay, this is a way to solve these first order linear differential equations. And basically what you do, you multiply by this function. I'll call it mu, which is also a function of r. And we can use the fact that property of the derivative, where you can split the product like this. And in this case, we would have that u is mu and v is tau. Knowing this, we see that u is mu and u prime is, which is also mu prime, is 1 over r times mu. So now we have a little differential equation which we can simplify. You can see that I got this by splitting the derivative d mu over dr. And we see that these are equal on both sides, so actually mu of r is actually just r. Great. And now with this part of the formula, we can combine this together, write our equation in this form. Now we want to find the shear stress. We can rearrange the terms. Integral with respect to r. There's going to be a constant left over from the integral. We can plug in r, so mu equals to r. We solve the integral. It's just r squared over 2. Nice. But we do not know c, so we need a boundary condition. And if you remember from earlier, the shear at r equals 0 is 0. There's no shear in the middle. So tau 0 equals to 0, which is equals to, and we have division by 0. So the only way that this would not blow to infinity is if c is equals to 0. So c is equal to 0. And now we have our final formula. Okay, now that we have this formula, we can start to find the formula for the pressure drop. Just for a warm-up, I'm going to start with a Newtonian fluid, and we will derive the well-known Hagen-poiseuille equation. The shear stress of the fluid for a Newtonian fluid is given by this formula, which is Newton's formula for the viscosity. Basically what it says is that the shear stress is proportional to the shear rate with a constant term, which is the viscosity. Okay, and now we want to find the velocity profile, so we can substitute. And now we have to integrate on both sides. There's only r, which will become r squared over 2, plus a constant. And to find this constant, we can use the condition that at the walls of the pipe, the fluid does not move. So u of r equals 0, where r is the radius of the pipe. And like this, we find the, which is minus gr squared divided by 4 mu. And we have our formula for the velocity. Now, to find the formula for the pressure drop, the Hagen-poiseuille formula, we need Q, the volumetric flow. So to find the volumetric flow, we will have to integrate the velocity over the cross-sectional area of the pipe. So this has to be done in cylindrical coordinates. Okay, we can already simplify the d theta part, since the formula does not depend on theta. We can write it like this. We can take this out of the integral, and we are left with this. Okay, now the bottom bound 0, because if you plug in, yeah, you see it all goes to 0, then we're only left with this upper bound. Okay, but now we just have G. We would want to write it down as delta P over L. So this assumes that the pressure decreases linearly over the length, over a certain length of the pipe. So I'm going to isolate G. Okay, and then if I write G like this with delta P, and I can bring L on the other side. And here we have the classical Hagen-poiseuille formula for the pressure drop of a Newtonian fluid. There's a negative term here because indeed the pressure drops, so delta P is negative. But we can also just remove this, since we know that it's a drop in pressure. So here's the formula. Okay, now that the warm-up is done, we are ready to go to the power law fluid, the pressure drop of the power law fluid. So what's different for this one is that the shear stress does not follow Newton's law, where K is the flow consistency index, and N is, of course, the power law index. Okay, just like last time, we're going to isolate U. And tau is G times R over 2. So we do the integral like last time. I'm going to take out all the constants. And now it's simply a polynomial. Okay, this term here, we can rewrite it like this, which is going to come in handy later. And now we have to find C. Like this, okay. And now we know that C is minus all of this. And once again, we have our velocity profile. Now we are going to get the volumetric flow. Okay, and now the lower bound gives 0. Upper bound, we find this. And the term inside here, we can simplify it, make it look a bit nicer. Cool. And now we can plug it in our main formula. So we have this minus because it's a pressure drop. And you will notice that the n plus 1s are going to cancel out very conveniently, as well as the 2. And we're left with this. Okay, now all that's left is to isolate G and rewrite it as delta P over L. So we will isolate G. We can actually remove the minus because we know it's a pressure drop. Okay, you'd notice that if you replace n by 1, you get a Newtonian fluid where mu equals k. Now we do the exponent thing to the power of n and delta P. So here we have it, the pressure drop of a power law fluid. And if you want to use another type of non-Newtonian fluid, then you just have to replace the shear stress by the appropriate formula.